Imagine a tool that can slice through steel with the precision of a scalpel, powered not by fire but by pure plasma. This is the hydrogen plasma torch, a machine redefining industrial cutting with speed, accuracy, and efficiency. For educational purposes only, full disclaimer on description. The hydrogen plasma torch begins as a precisely engineered steel and ceramic cylinder, resting on a lab table. Its polished housing reflects bright overhead lights, waiting for assembly that channels immense hydrogen power. Engineers carefully insert copper electrodes into the central chamber. These electrodes gleam with orange-gold highlights, aligned for perfect conduction. Their job is to focus electricity that transforms hydrogen into intensely hot plasma arcs. Next, technicians attach coolant channels, looping around the electrode housing. Tubes snake outward, carrying chilled water. This keeps the torch stable, preventing overheating when it later unleashes scorching jets of plasma. A reinforced ceramic insulator is fitted snugly inside. White and polished, it separates critical components, stopping electrical leakage. Its smooth surface is designed to withstand heat that would melt ordinary materials instantly. The power supply unit is connected by thick braided cables. Their insulation shines matte black, carrying massive electrical currents into the chamber. Energy here becomes the spark that transforms simple hydrogen gas into blazing plasma. Hydrogen tanks are wheeled in, silver cylinders with safety labels marked in red. Valves are checked twice, regulators adjusted carefully. The stored gas is pressurized, waiting to feed the chamber for plasma ignition. Precision nozzles are installed at the tip of the torch. Machined from hardened steel, they taper to microscopic apertures. Through them, plasma bursts forth, narrow, focused, and sharp enough to cut metal sheets. Cooling fans whir to life, mounted around the casing. Their blades spin fast, ensuring airflow across internal systems. Without cooling, the entire apparatus could overheat within seconds, collapsing under plasma's raw energy. The main power switch is flipped. A hum rises, deep and steady. Electricity surges through copper wires, charging the electrodes. The entire room vibrates slightly, a sign of energy building inside. Hydrogen valves open with a hiss. Gas flows smoothly into the chamber. The faint smell of clean, sterile hydrogen lingers in the air as technicians monitor flow meters for exact consistency. A high-voltage trigger is pressed. A flash ignites between electrodes. Instantly, hydrogen atoms strip apart, forming a brilliant jet of plasma. The torch head glows, releasing light brighter than molten metal. The plasma stream exits the nozzle like a blade of light. White hot, edged with blue, it roars. Its temperature climbs above 20,000 degrees Celsius, capable of slicing through nearly anything placed before it. A steel plate is moved into position. Plasma touches its surface, and instantly sparks fly. The steel glows orange, melting into clean lines as the plasma torch cuts with surgical precision. The robotic arm sweeps across the plate smoothly. Sparks cascade downward like fountains. Behind it, the steel is left with sharp, clean cuts, edges so precise they need no additional grinding. Cooling jets engage, spraying mist across the steel. Steam rises, clouding the air briefly. This prevents warping and ensures the metal retains its structural integrity after being exposed to extreme heat. Technicians check readouts during operation. Temperatures stabilize. Gas flow is steady, and electrode wear is minimal. Every parameter confirms the torch is working efficiently, proving its engineering design under intense stress. The robotic arm accelerates, testing speed. Plasma maintains a straight, stable jet. Even as the arm moves faster, the cuts remain flawless. This shows the torch can handle high-throughput industrial production lines. Engineers test angled cuts. The robotic arm tilts, slicing steel diagonally. Final endurance trials begin. The torch runs continuously for hours, slicing steel plates one after another. Temperatures remain steady. Efficiency holds, proving the system's readiness for real-world heavy industry deployment. Engineers switch from steel to titanium. Plasma slices through the stronger alloy with ease. Sparks burn brighter, but cuts remain perfect. This demonstrates the versatility across metals used in aerospace and defense. Another trial uses layered composite sheets. Plasma maintains control, cutting cleanly without fraying materials. This suggests applications in future lightweight construction, where precision on complex composites is critical for performance. The torch is integrated into a larger automated system. Conveyors move steel plates forward, robotic arms guide the plasma, and sensors monitor everything. It is now part of a streamlined production line. Power consumption is analyzed. Despite extreme output, efficiency is optimized. Energy use is lower than expected, thanks to electrode design and cooling systems. This makes the torch both powerful and economical. A digital log records every operation: cut time, gas flow, electrode lifespan. Data streams into computers, forming charts and graphs. Engineers review performance to refine efficiency for future production runs. The system is powered down. Hydrogen valves close, electrodes cool, plasma vanishes.